Welcome to G Fun Facts Online. Today we are stripping away the complexity of orbital mechanics to reveal one of the most fundamental, yet visually spectacular events in our solar system, planetary opposition. It is a moment of cosmic alignment that has historically unlocked the secrets of the universe's scale and continues to drive the rhythm of modern space exploration. Let's dive straight into the details. At its core, a planetary opposition is a geometric arrangement. It is a precise lining up of three celestial bodies: the Sun, the Earth, and a planet. This straight-line configuration is scientifically known as syzygy. But to understand why this matters, we first have to distinguish between the two classes of planets relative to Earth. We have the inferior planets and the superior planets. The inferior planets are Mercury and Venus. Because they orbit closer to the Sun than Earth does, they can never be in opposition. They can never be behind us relative to the Sun. From our perspective on Earth, Mercury and Venus are always tethered near the solar glare, oscillating between being a morning star or an evening star, but never fully opposite the Sun. The main characters of today's topic are the superior planets: Mars, Jupiter, Saturn, Uranus, and Neptune. These worlds orbit beyond Earth, and they are the only ones that can reach opposition. When a superior planet is at opposition, Earth passes directly between it and the Sun. If you were standing on the surface of Earth during this event, the planet would appear exactly opposite the Sun in the sky. As the Sun sets in the west, the planet rises in the east. At midnight, the planet reaches its highest point in the sky, known as the meridian. And as the Sun rises in the east the next morning, the planet sets in the west. This all-night visibility is the first hallmark of an opposition. So why does this happen? It comes down to orbital geometry. Earth moves faster in its inner orbit than the superior planets do in their outer orbits. You can think of Earth like a race car on an inside track. Periodically, we lap the slower outer planets. The time it takes for Earth to lap a planet and return to that same alignment is called the synodic period. For Mars, this happens every 780 days, or about 2 years and 2 months. This is actually the longest gap between oppositions, because Mars is moving relatively fast compared to the distant giants, making it harder for Earth to catch up. For Jupiter, Earth laps it every 399 days, roughly 13 months. For Saturn, it happens every 378 days. And for the distant worlds of Uranus and Neptune, the synodic period is only slightly longer than an Earth year, because their movement is so slow that Earth returns to alignment almost as soon as it completes a full orbit. Now, for the amateur astronomer, opposition is the prime time for viewing. There are 3 specific optical and geometric effects that conspire to make planets look their absolute best during this window. The first is perigee, or the closest approach. Opposition almost always coincides with the planet's closest physical point to Earth. Because the planet is closer, its apparent diameter in a telescope increases significantly. This effect is most dramatic for Mars. At its farthest point, known as conjunction, Mars looks like a tiny, featureless dot. But at a favorable opposition, its disk swells to over 25 arcseconds. This allows backyard telescopes to resolve the white, polar ice caps and dark surface features like Syrtis Major. However, not all oppositions are created equal. Planetary orbits are elliptical, not perfect circles. If Earth passes Mars when Mars is near its perihelion, which is its closest point to the Sun, the gap between our worlds is minimized to approximately 35 million miles. These are called perihelic oppositions or superoppositions. But if the alignment happens when Mars is at aphelion, its farthest point from the Sun, the distance can be nearly double, around 62 million miles. This is an aphelic opposition, where the planet appears much smaller. The second visual benefit is full illumination. Just as a full moon is fully illuminated because it is opposite the Sun, a planet at opposition shows a full phase to Earth. We see 100% of its day side. The shadows that usually highlight craters or cloud decks vanish. While this can sometimes make the view look flatter, the sheer brightness compensates for the loss of shadow contrast. The third visual phenomenon is perhaps the most fascinating. It is called the opposition effect, or the Seeliger effect. This is where a planet or moon surges in brightness disproportionately more than can be explained by distance alone. There are 2 mechanisms at play here. The first is shadow hiding. On a rough surface, like the Moon or Mars, rocks and dust grains cast tiny shadows. When we view the object from an angle, these shadows darken the surface. But at opposition, the Sun is directly behind our heads. The shadows are cast directly behind the objects that make them, effectively hiding them from our view. The result is a sudden brightening. The second mechanism is coherent backscatter. This is a quantum mechanical effect, where light rays scattering off microscopic particles interfere constructively when reflected directly back toward the source. The Seeliger effect is most stunningly visible on Saturn. The icy particles of its rings brighten intensely in the days surrounding opposition, often outshining the globe of the planet itself. Beyond the visual spectacle, Oppositions played a critical role in the history of science. Before the age of radar and spacecraft, these events were the only tools astronomers had to measure the scale of the cosmos. In the 17th century, astronomers knew the relative spacing of the planets thanks to Kepler's laws. They knew Jupiter was 5 times farther from the Sun than Earth, but they didn't know the absolute scale. They lacked the astronomical unit, or AU, which is the distance from Earth to the Sun. In 1672, astronomers Giovanni Domenico Cassini in Paris and Jean Richet in French Guiana engaged in a historic experiment. They waited for the opposition of Mars. Because Mars was close, viewing it from 2 distant points on Earth produced a measurable parallax, a slight shift in Mars' position against the background stars. Using this parallax angle and the known distance between Paris and Cayenne, they used trigonometry to calculate the distance to Mars. Once they had that single number, Kepler's ratios allowed them to unlock the distance to the Sun and every other planet. They calculated the astronomical unit to be roughly 140 million kilometers, which is remarkably close to the modern value of 149.6 million. A few years later, in 1676, the Danish astronomer Ole Romer used Jupiter's opposition to solve another fundamental mystery. He observed the eclipses of Io, Jupiter's innermost moon. He noticed a pattern. When Earth was approaching opposition, moving toward Jupiter, Io's eclipses happened earlier than predicted. When Earth was moving away from opposition, the eclipses lagged behind schedule. Romer realized the clock of Io wasn't changing. The light was taking longer to reach Earth when Earth was farther away. By calculating the time delay relative to the Earth's orbital diameter, he provided the first quantitative proof that the speed of light is finite. In our modern era, oppositions dictate the rhythm of interplanetary exploration. They are inextricably linked to launch windows, specifically the Hohmann transfer orbit. To send a spacecraft to Mars with the minimum amount of fuel, engineers don't point the rocket directly at Mars. They launch the spacecraft into an elliptical orbit that touches Earth's orbit at one end and Mars' orbit at the other. For the spacecraft to arrive at Mars, the planet must be there to catch it. This requires launching roughly 3 to 4 months before opposition. Since oppositions occur every 26 months, optimal Mars launch windows also open every 26 months. This is why you see fleets of probes leaving Earth in waves. For example, the summer of 2020 saw the launch of NASA's Perseverance, China's Tianwen-1, and the UAE's Hope, all targeting the favorable alignment surrounding the October 2020 opposition. If a space agency misses this window, they cannot simply launch a little late. The geometry breaks, fuel requirements skyrocket to impossible levels, and they must wait 2 years for the next alignment. Looking ahead, the next decade offers several must-see events for observers. Mars oppositions are the most anticipated because of the dramatic size change. In January 2025, we will see a solid mid-range opposition with Mars high in the northern sky. February 2027 will be an aphelic opposition, meaning Mars will be far and small, making details difficult to see. However, the cycle turns favorable again on June 27, 2033, with a bright perihelic opposition. But the date to mark on your calendar is September 15, 2035. This will be the big one. It will be a super opposition comparable to the historic events of 2003 and 2018. Mars will be dazzlingly bright and large, revealing sharp details like the Valles Marineris Canyon system. Saturn also has a special event coming up. While it reaches opposition annually, 2025 is unique. In March and September of 2025, Saturn will undergo a ring plane crossing. Earth will pass through the plane of Saturn's rings, causing them to appear edge-on. For a few weeks, the majestic rings will seem to disappear into a razor-thin line, leaving Saturn looking like a lonely, naked ball. This is the best time to hunt for faint moons that are usually glared out by the rings. For Jupiter, look to January 10, 2026. Jupiter will reach opposition in Gemini, high in the winter sky for northern observers, likely offering the crispest atmospheric views of the decade. Finally, it is worth touching on the cultural perspectives. While science views opposition as a geometric inevitability, culture and astrology have long imbued these events with meaning. In astrology, an opposition is traditionally viewed as a point of high tension or polarity, a tug-of-war between two forces requiring balance. A Sun-Saturn opposition is often interpreted as a reality check, while a Sun-Mars opposition is associated with high energy and conflict. Conversely, a Sun-Jupiter opposition is seen as a time of abundance. Culturally, the Roman god Janus, the two-faced guardian of transitions, is spiritually linked to this concept, looking simultaneously east at sunrise and west at sunset. The opposition is a moment of full awareness, where the hidden nature of a planet is fully illuminated to Earth. In conclusion, a planetary opposition is more than just a date on a calendar. It is a convergence of history, physics, and beauty. It is the moment Cassini measured the solar system. It is the moment Romer timed the speed of light. And it is the window through which humanity flings its robotic envoys to distant worlds. When you look up at a planet in opposition, shining fiercely at midnight, you are seeing it at its closest, its brightest, and its most scientifically profound. Thank you for listening to G Fun Facts Online.